Okay guys, last time we were talking about some basics about measurement amplifiers and operational amplifiers, which were that an ideal operational amplifier has an amplification factor of infinity. That's strange somehow, but I also denoted in the last part that by doing some well-defined recoupling of the output signal to the input signal, we can define a very specific amplification factor for the whole system. So just let's look at those systems from a perspective not using operational amplifiers, so that you get the idea of those systems being general for many other systems also which deal with recoupling. So first thing is, what do we have? Standpoint from last time was we have some input signal. So let's just define our input signal Xe over here. Now that input signal will go through a plug over here, which produces some Xe line input signal, which then will be amplified by the operational amplifier, for example, or by any operational amplifier, which gives us an amplification factor of K line, as denoted in the last part. That will give us an output signal Xa. And now we want to do a recoupling. We want to couple some part of the output signal defined by some factor Kg back to the input signal. And now that coupling over here, that combining, should be a negative one, meaning that the output is subtracted from the input. Now, let's see what that means. For me, when looking at those recoupled, those feedback loops, I always get confused, because feedback loops implies some type of a regression, it's going on forever. The coupling goes on forever. We are in a loop. It's not clear what to do. For that purpose, we can think about the stuff quite easily. So what we want to know is the amplification factor of the whole system. We'll denote it with K without a line. So K is nothing else than the output signal divided by the input signal. For sure. That's the amplification of the whole recoupled whole feedback system we have over here. And now we can think of the different parts here. So what is Xa? Xa is Xe line times K line. That's how it is defined. That is how our operational amplifier or our amplifier works. So we have some Xe line times K line. Divided by what? Okay, by the input signal. So we know something about the input signal, which is the input signal over here is connected to the input signal line, the output, and somewhat that recoupling factor. So what we can write down is Xe line is nothing else than Xe minus the feedback line over here minus Kg times Xa. And now that simply can be flipped around, telling us that Xe is Xe line plus Kg times Xa. That is something we can plug in over here. So let's plug in over here and we get Xe line plus Kg times Xa. Okay, now we get a glimpse of hope to solve that loop problem. We see there's an Xe line in the numerator and the denominator. So let's simply go on and replace that Xa like we did beforehand, by XE line times K line. So we get XE line times K line over XE line plus KG times K line times XE line. Now we see we can just cross out that XE line. And that's awesome, because those quantities, we don't know about the exact behavior of XE line and XA and so whatsoever. But now we simply have crossed them out. We have deleted them from that desirable equation of knowing the amplification factor of the whole system K. And what we get is K line over 1 plus Kg times K line. So, normally for a real operational amplifier, for example, K line is something like 10 to the 6. We could plug that in, do a recoupling by a factor of 0.5, 0.2, by a factor of 2 or whatsoever, and by that define an amplification factor of the whole system exactly. But now let's do our assumptions for the ideal operational amplifier. For the ideal operational amplifier, that K line is infinite. So we get K line goes to infinity in that system, in that numerator and denominator system. So for getting a better insight, we just do some little calculation, dividing both numerator and denominator by 1 over K line, giving us 1 in the numerator and giving us 1 over K line at the first place in the denominator and dividing by K line plus Kg at the second place. And now it's obvious what happens when K line goes to infinity. That factor over here goes to 0. And we get 1 over Kg. That means doing a recoupling by a factor of 0.5 will produce an overall amplification of the whole system by a factor of 2. We can choose to recouple the whole signal and we'll get an amplification of 1 and so on. We are free to choose the amplification of our whole system by easily defining the amount of feedback from the output to the input. That's great. Why is that great? Because with which operational amplifier out there, we can construct a system with any amplification we want to have. That's the other thing why it's great to have an amplification factor which you can set up yourself. It's great because you are free to choose that recoupling factor, and by that free to choose your amplification. And that gives you the freedom of buying any operational amplifier and nevertheless have any amplification factor you want to have. For sure, on the upper limit, there's that K line of the operational amplifier itself. You can't go over that. Amplification can't be more than that. For sure, going to the downside, it makes no sense to have no amplification most of the time, or even to have a negative amplification, meaning a reducement of your input signal. Okay, now let's look at a simple example of an electrometer amplifier system. That's the usage of that theory within a real electrical circuit, meaning we have our operational amplifier in that system. which has an input signal UE relative to the ground, and we have a feedback loop which takes the output signal, divides the output signal in two parts, and gives us the output signal in the end. Okay. Looking at that circuit, it looks strange at the first place, but remembering the stuff we were doing beforehand, we realized that by using that voltage divider over here, we use a subpart, some ratio of our output voltage, and couple it back, recouple it to our input and subtract it there, because we couple it to the minus side. That's it. So remember, there's some external voltage which drives the operational amplifier, which gives out the output voltage UA, and part of that output voltage, and that part is defined by the ratio of R1 to R2, is coupled back to that input side over here. How to deal with such electrical circuit, how to define that amplification factor of such a system. Okay, coming back to our beforehand denoted simplification of the system, we were writing down something like our XE line equals XE minus XG, the part which was coupled back, which is KG times XA. Now, using that amplification factor of beforehand, we know that XA is nothing more than XE over KG. You remember, for an amplification factor K line of infinity, we get an amplification of 1 over Kg. So, plugging that stuff into that equation over here, we realize Kg crosses out. XA is replaced by XE. We realize that gets to 0. Meaning, that thing which goes in here, the XE line, that goes into the amplifier, is always 0. That means that thing over here, that voltage between those two plugs is 0 when we do a feedback loop like that. That holds in general for all recoupled, for all feedback loops of that kind. We just derived it beforehand, that we have an amplification factor of 1 over Kg. And so we now realize that when plugging that in, that signal which goes into the operational amplifier has to be 0. In general, but also for the electrical circuit. That is an important thing. That resolves some of the issue I always have about those systems, because having 0 at that input is the only resolution of the problem of those loops. If there would be some voltage at the input region over here, we would get some output voltage, which is the result of amplifying that signal, and that signal, that amplified signal, would be coupled back. And if we still would have some signal over here, that would always go the way round and amplify itself and amplify it and amplify itself until we get to some no resolution, no solution outcome, because we don't know what that means. It's always amplifying itself and always amplifying itself. In the end, that such a system has to go to infinity. But when there's 0 at the input, that problem is resolved. And our equations tell us there has to be 0 input. To be honest, looking at the script in detail, the calculations for that electrical circuits are done in detail without assuming that that difference voltage over here, UD, is not 0. Those calculations aren't very complex, but we don't need them over here because we know we have a recoupling, we have a feedback loop, it has to be 0 over here. But on the other hand, it's nice to know that when doing the real, more sophisticated calculations using the electrical circuit, it also has to be 0. But that's some standpoint we can have to look at our system and to solve our problem. So, what is our problem at all? We want to have the amplification factor of our whole system again, K. So, that K again is UA over UE. That's obvious. Now let's think about that electrical circuit and how to connect UA with UE. We can do some mesh over here, some circuit, which goes this way. We are free to do so. Now let's sum up all the voltages in here. And since we know electrical circuits and electrical behaviors and theories, we know all the voltages within this circuit have to add up to 0. So let's see. What that gives us is UE plus. Okay, we have 0 over here, plus 0. Let's just write it down. That's the voltage between those two plugs. Now we are on the other side. We go along, we go along, we go along. That's the voltage which falls over R2, which is the part of the voltage UA which falls over R2. So the last part we need is that voltage which falls over R2, and that is defined by the voltage divider, which divides the voltage UA which falls along R2 and R1 and R2, and we only use that part which falls over R2. So we get minus UA times R2 over R1 plus R2. That has to be equal to 0. Now, putting that stuff around, we get UE equals UA times R2 over R1 plus R2, and that tells us UA over UE equals R1 plus R2 over R2, and that tells us over here that we have 1 plus R1 over R2 as the amplification factor for our whole electrical circuit over here. So the main assumption for that was that difference between those two input voltages, that difference voltage has to be 0 because of the feedback loop. That's the important stuff. And by that we can do some meshes over the operational amplifier, and by that connect the output voltage to the input voltage. That's the whole trick about dealing with electrical circuits, having electrical amplifiers, having operational amplifiers in it. There are some other tricks, which I'll denote here, which is not only that the difference voltage is 0, but also that the currents flowing into that operational amplifier have to be 0 nearly, at least nearly. Why is that so? Because there's no voltage, there's no current that can flow along a line where there's no voltage as the first thing. The next thing is thinking about operational amplifier as to be ideal. We know that input resistance is nearly infinity. And that means no current can flow into that operational amplifier any which way. Okay, so that was the first simple example of an electrical circuit using an operational amplifier. In the next part, I will talk about some other electrical circuits using electrical amplifiers, using operational amplifiers, which are somewhat important and at least interesting to know about. Till then, have fun.